In this video, we will look for the few applications of the 3D Maxwell distribution, Maxwell speed distribution, and we will use it mainly to determination mainly for the determination of the average values of the perfectly ideal gaseous system, average speed values of the perfectly ideal gaseous system. And what we are going to do is we are going to determine the values of the average C, this average of C squared, and from here we will find out the root mean squared average, and we will also find out the most probable velocity, or the most probable speed, right? And we will do all this using the 3D Maxwell speed distribution. We will do all this using the 3D Maxwell speed distribution, because we could have done the same for the 2D distribution. We could have done it using the 2D distribution as well, but as we know, it is more useful to do it in 3D, because ours is a three-dimensional world. It is more convenient to use the 3D distribution. We have to do it for the 3D distribution, 3D speed distribution. So we will recall what we derived for the 3D Maxwellian speed distribution. Was dnc by n was 4 pi m by 2 pi kt whole to the power 3 by 2 c squared e to the power minus alpha c squared dc. And the first thing that we are going to determine is the average C. And we know that to determine the average speed of the Maxwell speed distribution, the way we proceed is we have to take the integral in all space, that in this case would be c equal to 0 to c equal to infinity, c times number of molecules in the speed range c to c plus dc, and integrate so that we can integrate and dnc, and we will integrate dnc from c equal to 0 to c equal to infinity dnc. Now if we are using the normalized speed distribution, this c equal to 0 to c equal to infinity dnc was actually equal to n, and we can show this from our previous videos, that this was actually equal to n for a normalized speed distribution. Thus the average speed came out to be 1 by n integration of 0 to infinity, and we will have to just put this speed distribution formula right here, and we copy the entire thing, paste here, let's put it here, and we will move this right here, and there will be a 4 pi n here, and we can cancel out the n's and take out the constants. This is 4 pi m by 2 pi kt whole to the power 3 by 2 and we will integrate c squared e to the power minus alpha c squared dc and 0 to infinity. Now this alpha, we know that this alpha is actually nothing but m by 2 kt. So I already wrote alpha, and generally this alpha is known to us from the previous video. So it all boils down c squared, and we had an extra c here, so this wasn't actually c squared, this is actually c cubed. And we have faced this integral, let's call this integral as I, and we have faced this integral in the past. Somewhere in the past we have faced it, and this is actually our integral that needs to be solved. And the way to do this was actually starting with a standard process of substitution, integration by substitution. We will take alpha c squared as t, and 2 alpha c dc was actually dt, and c dc was dt by 2 alpha, and we had a c cube in the polynomial part, so we could write c squared into c e to the power minus m c squared e to the power alpha c squared dc, right? And we had I as we would have c squared here, and we could have multiplied and divided by alpha, and alpha c squared was t, and c dc was e to the power minus t dt, and this was c dc was actually dt by 2 alpha, so there was a 2 alpha right here, and we had 1 by 2 alpha squared. We had 0 to infinity t e to the power minus t dt. Alpha was a constant, and 1 by 2 depending on temperature, so temperature was constant, and t to the power minus t, we know that this is actually the gamma of 2, and gamma of 2 was 1 factorial, and 1 factorial was 1, so this is 2 alpha squared, 1 by 2 alpha squared, and the average c now turns out to be what? 4 pi alpha upon pi whole to the 3 by 2 into 1 by 2 alpha squared, 1 by 2 alpha squared, and we have written the entire problem in terms of alpha. We will substitute it right in the last step, and we had 4 here, 4 pi minus pi 1 minus 3 by 2, and 2 was coming, so 4 and 2 cancel to be 2, so we have 2 here, and alpha to the power 3 by 2 minus 2, so this is 2 pi, this is minus half minus half, right? So we had root pi alpha, and we put the value of alpha, which is actually alpha was m by 2 kbt or kt, whatever. Since we used kt, we will go for kt. K was the Boltzmann constant, and if we take this 2 inside the root, it will come in as 2 squared, so this was actually 2 squared times 2 kt by pi m, and we have the famous formula for the average speed of the Maxwell speed distribution was this. Also remember that this is actually the average speed of one molecule. This was square root of 8 kt by pi m. If we had to find the average speed per mole, then this m was like the mass of the gas, a gas molecule, or let's talk about it simply. This m was the mass of the gas molecule. If we had to express this mass of the gas molecule in terms of the molecular mass, the average speed can also be, because remember that k was actually r by na. So when you put k, so when you put average c is actually square root of 8r t by pi na times m. This na times m actually gives, remember that mass of one molecule by molecular mass is actually the Avogadro number, and sorry, and we had here the 8 RT upon pi m, and Na times m was actually the molecular mass of the gas, because m was the atomic mass of the gram molecular mass of the gas concerned. So this is our formula. The second thing that we are going to determine is actually the average c squared, the expression for average c squared. And we defined here something called the root mean square velocity. And when you say root mean square, we actually go from this side to this side, from right to left. So first we had a speed, we square the speed, then we take the mean, and then we take the root. So that is actually the root mean square. To find the root mean squared, we need to determine this average c squared. The average c squared was actually given by the same way as we know for the average formula, is actually c squared dnc upon 0 to infinity dnc. Again, in dealing with the normalized speed distribution, the denominator would just be n, and this should be c 0 to infinity c squared dnc, right? So this is 0 to infinity db 4 pi n m by, so no, alpha by pi whole to the 3 by 2, and c squared e to the power minus alpha squared dc. And we had 1 by n, the 1 by n and 1 by n was cancelling out, and we had 4 pi alpha by pi whole to the power 3 by 2, 0 to infinity c to the power 4 e to the power minus alpha c squared dc. Now the problem, again we have to solve this integral, and this integral is a even function, that is the second even function, right? Second even function of the series, and we have solved for this even function, and we shall solve for it again. This even function was actually the mod of the second derivative with respect to alpha of half root pi upon alpha. Again we will be jumping a few steps. The first derivative gave us, which is what we gave, the first derivative was actually root pi by 4 alpha to the power 3 by 2, and we shall take root pi by 4 a common, and we had 3 by 2 alpha to the power 5 by 2 in the denominator, and this came out to be 3 root pi 8 alpha to the power 5 by 2. So this is our expression, and when we had to find the value for the average C square, what we had to do was 4 pi alpha by pi whole to the power 3 by 2, 3 root pi by 8 alpha to the power 5 by 2. We shall evaluate the result, and here we can see the 2 cancelling out, and this 3 by 2 was getting cancelled in the denominator, was cancelled by 3 by 2 in the numerator, and the pi was getting cancelled out totally, and there was alpha to the power 3 by 2 minus 5 by 2 into 3 by 2, and this actually came out to be 3 by 2 alpha, and alpha came out to be m by 2 kt. 2 was getting cancelled, and this came out to be 3 kt upon m. Average C square came out to be 3 kt by m. If we had to talk about the root mean squared velocity, this would be the square root of this average C squared, and this came out to be 3 kt upon m. Now if we had to express this formula and replace this mass of each molecule of the gas with the molecular mass of the gas, then or the gram molecular mass of the gas, right, we can actually use the relation K equal to R upon Na, and this would convert this into 3 RT by m. M is the gram molecular mass of the gas. Right, so we had derived the first two values, the root mean squared and the average C values, and the third value to determine was the most probable velocity. So before we determine the most probable, not velocity but the speed, the most probable speed. The most probable speed, let's go back to a distribution function and write it again. Our distribution was something like 4 pi m by 2 pi kt whole to the power 3 by 2 c squared e to the power minus m by 2 kt, let's not write alpha this time, dc, and thus our density function, which we discussed in the first class, looked something like this. This is actually a density function, and this looked like 1 by n dn dc, and this came out to be 4 pi m by 2 pi kt whole to the power 3 by 2 mc squared by 2 kt. And this was actually a density function. If we are able to maximize or minimize this function, this is actually a probability function, and the maximum value of this function would give us the conditions of the maximum value of this function would give us equations for which we can solve the value for this most probable speed c, right? Can we do that? And what is the idea, what is the way to do it? If we call this fc as 4 pi m by 2 pi kt whole to the power 3 by 2 c squared e to the power minus mc squared by 2 kt, what we need to do is just differentiate this function, put it equal to 0, differentiate this function again second, and say that this is less than 0. Can we do that easily? We can do that very easily. What should be the first differentiation with respect to c? That should be dc ddc on 1 by n dnc dc. Take out the constants and we have, so now we will write alpha for our own convenience. We will write alpha by pi whole to the power 3 by 2, and the differentiation would be on ddc on c squared e to the power minus alpha c squared. And unfortunately there is no trick this time. We have to go for the complete solution. We have to solve this differentiation. The first term was e to the power minus alpha c squared ddc on product rule, this is product rule, c squared. The second term was c squared ddc on with plus sign e to the power minus alpha c squared. And there would be 4 pi alpha by pi whole to the power 3 by 2, this is 2c e to the power minus alpha c squared plus c squared minus 2 alpha c e to the power minus alpha c squared, and this was actually equal to 0. Since these were constants, we can only focus on the substance in the square bracket only, and we would have e to the power minus alpha c squared two c minus 2c cubed uh, 2c cubed alpha, right, 2c cubed alpha equal to 0, and we had c e to the power minus alpha c squared 2 minus 2c squared alpha equal to 0, and this is our equation for maxima or minima. Now before we go on to the discussion about the 3D Maxwell, to the solution of this problem, we shall discover what should be the graph of this function look like. So the graph of this function with fc on the y-axis and c on the x-axis looks something like this. And we shall discuss why it looks like this later on. it looks something like this, right? But this is actually the origin. It looks something like this. So what are the values of C for which this equation was getting satisfied? Case 1, when C equal to 0. First case, C equal to 0. This is again a trivial case because this is actually representing this point. This is actually the origin. That means this actually implies that the molecules which have a speed 0 in the system are almost 0, that is negligible. There are almost no molecules with speed 0. So this is actually this is actually a minima. Okay, what is the second situation? The second situation is e to the power minus alpha c squared is equal to 0, and this is only possible when 1 by e to the power alpha c squared this is equal to 0, and alpha is a constant quantity dependent only on temperature, right? Alpha was m by 2 kt, only dependent on the temperature and nature of the gas, so that cannot be 0. That means C was tending to infinity, a large number, and for that also we actually achieve a minima here. We can see from the graph above that this, when C was actually tending to infinity, this was actually tending towards the minima. That is, molecules with speed tending to infinity were also very less in comparison. Right? And now we had the case 3. This is all being done graphically. Case 3. What should be the case 3? Case 3 would be the most probable velocity, which should be this point. We will be determining the speed at this point. This should be a CMP. How do we get it? We get it from this expression. 2 minus 2 c squared alpha, that was equal to 0, and C came out to be c squared came out to be rather 1 upon alpha, and since we are talking about speeds, it should be non-negative. This should be 1 by root alpha. Putting the value of alpha, we get root kt by m, and again making a substitution, this should be 2 RT by m. This is actually our most probable speed, and this is actually our most probable speed. And for this we can say that this is actually a maxima from the graph. We can also go ahead and perform the second derivative and put the value of this c in the second derivative and apply the second derivative test. We will see that the second derivative will definitely be less than 0, and we can also state graphically, since this graph had no other maxima or minima, had 2 minima and 1 maxima. This is actually a maxima which we found out, and no other point where the derivative was becoming 0, or no other critical point, then definitely this is the maxima point, and we can clearly justify that this is our point that we were looking for, and this is the maxima. This is our maxima. And so we had all our 3 average values in our we have calculated the value of all the 3 values as promised in the beginning of this video.